All right, so I forget where exactly I cut out, but yeah, let's not read too much into it here. It's happened before. So we need to find total energy, right? Total energy first. And so I've got a 5 watt laser, and I know that 1 watt is joule per second. So we want to kind of get rid of watts and get that over into joules per second. So because 1 watt is 1 joule per second, right? We've basically got a zero point 0.5, right, joule per second. That's how much our laser is giving off. And we run that laser for 10 seconds. So basically, our laser is giving off 5 joules of energy. Now we need to find how much energy is there in 1 photon of this light, right, of 585 nanometers. And so we know, right, energy equals Planck's constant speed of light all over my wavelength. For this equation, though, I need to use my wavelength in meters. So 585 nanometers, right? We know 1 times 10 to the 9 nanometers are in 1 meter. So I've got 5.85 times 10 to the minus 7 meters. All right, so energy equals Planck's constant 6.626 times 10 to the minus 34 joules times seconds. Speed of light 3 times 10 to the 8 meters per second. All over my wavelength, 5.85 times 10 to the minus 7 meters. So we do some unit analysis, multiply, seconds cancel out, we divide, meters cancel out, we're left with joules. All right, and so we're going to find the energy of 1 photon of light. All right, is, let's see, divide that by 5.85 times 10 to the minus 7. Yeah, we get the energy for 1 photon is 3.3979 times 10 to the minus 19 joules, and that is per single photon. So when we did this problem in class, somebody was asking, what equation do I use for the last step? This is not really a place where we need an equation for the last step. It's more just dimensional analysis to see for the last step I have 5 joules of energy, and I need to know how many photons I would need to make up that energy. So 5 joules of energy, I know for every 1 photon, right, it brings 3.3979 times 10 to the minus 19 joules. So we divide, joules cancel out, and we're going to be left with like 1.47 times 10 to the 19 photons needed, right, to provide us with that much energy, the 5 joules of energy for that question. How many calculation questions are on the exam, right? It's probably the last like 5 or 6. There's going to be, if you are in the Monday, Wednesday, Friday class, it's going to be probably 5 questions, 5 calculation questions. If you're in the Tuesday, Thursday class, it's probably going to be like 7 to 8 calculations, just because the Tuesday, Thursday is an 80-minute session. It's a little bit longer. So your exam's usually a little bit longer than the Monday, Wednesday, Friday, which is a 50-minute class. And then someone asked for question 12, so I'll go back and do question 12. And then Tina asked me to leave, right? Told me I needed to get kicked out of leave you alone. So, yeah, question 12, right? Which of the set of quantum numbers cannot exist? So, right, n can be anything 1, 2, 3, 4, 5 to infinity, right? Oh, okay, let me just go back real quick. No, Sarah, the 3.39 times 10 to the minus 19 is not a constant. Right, that is the energy for one photon of light that has a wavelength of 585 nanometers, right? That's where this number came from. This is the energy of this photon of light. So if the wavelength changed, the energy of that light would change. So yeah, this energy was not a constant. This energy is for this specific wavelength of light. 585 nanometers is this is the energy for one of those photons. If this was like 600 nanometers or 400 nanometers, that energy would change. So yeah, that energy, we found that from our wavelength. It's not a constant. Right? L can be 0 to n minus 1. And from there, we can, and then ML can be negative L to positive L. So if we look, right, if n is 3, L can be 2. That's fine. N is 2, L is 1. That's fine. N is 4, L is 3. That's fine. 4 to 2, that's fine. 5 to 4, that's fine. If L is 2, however, ML can just be negative 2 to positive 2. So that disqualifies that. So that cannot exist. If L is 1, that checks out. L is 3, ML can be 2. If L is 2, ML can be 1. And then if L is 4, sure, ML can be minus 3 because it can be within minus 4 to plus 4. So that checks out. So just choice A there is incorrect because our uh, basically our orientation, it's telling us, right, an orientation of a d orbital that does not exist with that combination of numbers. Yeah, so let's see. Stop recording.